Hello everyone, this is Dr. Lennon, and today we're going to be looking at some uniform motion problems, which basically are just word problems involving our distance equals rate times time formula. So usually what you want to do is just create a chart to organize your information and try and write an equation. So let's go ahead and look at this problem. We have two truck drivers that leave a rest area at the same time. One's going east, one's going west, so they're traveling directly opposite each other. One is traveling west at 70 miles an hour. The other is traveling east at 60 miles per hour. How long till they are 325 miles apart? So what they're asking for is a time. So let's write our variable so that our answer will be that time. So let x equal time until they're 325 miles apart. So, what do we have? We have our time travel, our rate, and that will equal our total distance traveled if we multiply the time and the rate. So, I don't know, let's call the trucks just trucks A and B. I mean, you could name them other things, or we could call them E and W for east and west. I suppose maybe that's a little easier to remember. So we have the eastbound truck and the westbound truck. So they're both traveling for X hours. The westbound truck, or the eastbound truck, is traveling at an average rate of 60, the westbound at 70. And we know that the total distance between them, so the distance of the eastbound truck is 60 times X, the distance of the westbound truck is 70 times x. So this is how we write our equation, because we know the total distance has to be 325 miles apart. So if we add the two partial distances, 60x plus 70x, we get our total distance of 325. So 60x plus 70x adds up to 130x, and that still equals 325. And then we divide by 130. And we get an answer of 2.5 hours. So that's a pretty straightforward example. Some of the other ones will be a little trickier, but we're going to be using the same idea. So label a variable, organize your information in a chart, remember the distance equals rate times time equation, and go ahead and write down an equation given your information from the chart. So let's go ahead and look at this next example. We have Christopher and his parents. They live 115 miles apart, so that's a distance. They met at a restaurant between their homes, somewhere in between, to celebrate his mom's birthday. Chris drove for 1.5 hours while his parents drove 1 hour. Christopher's average speed was 10 miles faster than his parents' average speed. So what were the average speeds of Chris and his parent as they drove to the restaurant? So for this one, we want to let our variable represent one of the unknowns. So let's let x be the parent speed, and then x plus 10 would be the Chris's speed since it's faster. So let x equal the average speed of the parents. So what we have is, again, we can set up a distance equals rate times time situation. So we have Chris and the parents. We want to know a average speed, so that's a rate. So the things that were given, let's try and label those. So again, we have the we're going to have a time, a rate, and a distance. And we know if we multiply the time and rate columns, they should equal the distance. So the thing is, we know the total distance, but we don't know exactly where the restaurant is quite yet. We know the times traveled, so we know Chris drove for 1.5 hours and his parents drove for 1 hour, and we know how the rates are related. We know Chris drives for we know Chris is x plus 10 based on how we've written this. He drives 10 miles an hour faster than his parents, who are driving x miles per hour. So if we multiply across, remember, for the first one, we need to put parentheses around x plus 10 because it's more than one term, and 1 times x is just x. So here we know, again, the total distance between them is 115. So if you add the two partial distances, you get the total distance. So that's where our equation is going to come from. We know that 1.5 times the quantity x plus 10 plus x should equal our total distance of 115. So we just go ahead and distribute. So we get 1.5x plus 15 plus x equals 115. So 1.5x plus x adds up to 2.5x plus 15. That equals 115. And then we want to subtract 15 on both sides. So we end up with 2.5x equals 100. So we can divide by 2.5, and we get a speed of 40 miles per hour. So remember, that would be the parent speed. So the parents are driving at 45 miles per hour. So this is the parent speed. Whereas x plus 10 would be 50 miles per hour. And that would be Chris's average speed. And that's it for that problem. So a little bit trickier because we had a relationship between the rates of the two travels, the speeds of travel. So let's go ahead and look at another one. Okay, so let's have a look at this problem. So in this one we have Katie May walking to school. It takes her 30 minutes if she walks. If she bikes, it takes her 15 minutes. And we know that her speed is 3 miles per hour faster when she rides her bike versus when she walks. So we want to know what are the walking speed and the riding speed. So again, here probably we just want to let x be the walking speed, which will make the riding speed x plus 3. So we have Katie May here, just the one person, but we have her two different rates of travel, so maybe we should do it that way. We should do walking versus biking. So that's where we get our two. So we have walking and we have biking. And then we still have the same labels on the top, distance, rate, and time. Or I do it, time, rate, and distance. Doesn't really matter which order you write them in, so long as you make sure that when you multiply your rate and your time, you get your distance. So we know that when her x is her walking speed, and her speed when she rides her bike is 3 miles an hour faster, so x plus 3 is the rate there. And when she walks, it takes her 30 minutes. When she rides, it takes 15 minutes. Now, the thing here is the distance is the same since her distance from home to school is the same in either case. So basically, we can set the two distance columns equal here to get our equation. So we can set 30x equal to 15 times x plus 3. And that will allow us to solve for the value of x, which is her speed walking. So go ahead and distribute on the right. So we get 15x plus 45. So we want to move the x's to the same side, so we can do that by subtracting 15x. So we have 15x equals 45. Since x is being multiplied by 15, we can divide by 15. So we get x is equal to 3. Now, what units are those, in fact? This is a rate, and a rate is going to be the units of your distance divided by the units of your time. So her speed was in, or her distance was in miles. So, okay, so here's actually something that was going on here. We were a little bit lazy when it came to units because we were putting her time in terms of minutes, but her rate was given in terms of miles per hour. So actually, probably we want to use consistent units here. So why don't we go ahead and convert our minutes to hours and then go ahead and do the problem again? And because we're mixing units, so the numbers will not come out quite correct this way. So if we have 30 minutes and we multiply by 1 hour over 60 minutes, we see in fact that this is 0.5 hours. And if you do the same with 15 minutes times 1 hour over 60 minutes, we end up with 0.25 hours. So really what we should be doing is we should be replacing the 30 here and the 15 here with those rates of 0.5 hours and 0.25 hours. Otherwise, you're mixing hours and minutes in your problem, and your answer will not make sense from a unit perspective. So we need to change those and start back over. So we had a little mistake, and I was actually thinking about that before I wrote any of this down. So I should have paused for a second there before I began. But okay, so I forgot to change the chart. So this will not be 30x, but will be 0.5x, and this will now be 0.25 times x plus 3. So we have 0.5x here, and we have 0.25 times x plus 3. So 0.5x is going to be the same as 0.25 times x plus 3. The steps of solving this will work the same, so we begin by distributing. So we get 0.25x. 0.25 times 3 is 0.75. And then we want to subtract the 0.25x and divide. So we end up with 0.25. X equals 0.75. And divide by 0.25. And we should end up with x is equal to, I think this comes out to 3. Yep. So it comes out to 3, which actually I believe still came out to what we had, if memory serves. But anyway, at least we know the units are proper this time. So what are the units? The units here are actually now miles an hour, what we have been working with. So this is Katie May's walking speed. Which means if we added 3, we would get her biking speed. So x plus 3 would be 6 miles per hour, which would be Katie May's biking speed. So let me go ahead and let's look at one last example today, and we will leave off there. Okay, so in this last example today, we've got Hamilton who's traveling to Las Vegas, which is 255 miles from his home. On his last trip, he left his house at 2, and the first part was congested. And at 4, he was able to drive through the desert at a speed 1.75 times faster than when he drove in the congested area. So if he arrived at 6:30, how fast was he driving during each part of the trip? So we've got one trip here kind of divided into 2 segments. We've got segment 1, and then we've got segment 2, where he's driving faster. So in the first segment, if we call his speed x, then the second segment he's driving at 1.75 times x, 1.75 faster. So let x be the speed, or the average speed, on the first part of the trip. And then from there we can set up the same old chart that we're used to. So I don't know, we'll just call it leg 1, and leg 2 of the trip. And then we know that we've got our time, our speed, or we're using a rate here, our time, our rate, and our distance. So we know the total distance here. We know the total distance is 255. The time, we know the first part we're going x, and the second part we're going 1.75 times x. And then the rate, oh sorry, that was the rate, not the time, so I'm filling out the wrong part of the chart here. So x for the first part, 1.75 x for the second part. The time, well, he starts at 2 o'clock and it's congested until 4. So for the first 2 hours, he's driving at that rate of x. And then he arrives at 6:30. So from 4 o'clock to 6:30 is 2.5 hours. So 2 hours, 30 minutes is 2.5 hours. And the distance, again, you can multiply time and rate to get your distance. So we get 2x for the first part of the trip and 2.5 times 1.75x for the second part. And 2.5 times 1.75 comes out to 4.375. So we can just write this down as 4.375x if we want. So then if you add the two distances there, we know they come out to the total distance of 255 miles. So we know that 2x plus 4.375x has to add up to 255. So the left-hand side, both sides are like terms. So you can just add their coefficients and we get 6.375x equals 255. And then we want to divide by the 6.375. And we get our answer. X is 255 divided by 6.375, which is 40. So during the congested part of the trip, his average speed was, so let's write that down, average speed for leg 1, the congested part of the journey, and then 1.75 x is the, so that should be 70 miles an hour, I think. Yeah, 70 miles per hour is the average speed on the second leg, which was not congested. So the average speed for leg 2. So as you can see, usually these uniform motion problems, there's nothing to be scared of. You just have to pick your variable carefully and then go ahead and figure out your chart properly. And usually you're either going to get your equation from adding the two distances and getting a total distance or some version of that. So this is Dr. London signing off.